Here we go. What's our goal today? Yes. Learn. That's so cheesy. Okay. What's a system? A system is a group of at least two equations. And these two equations usually have at least two variables. Usually. Yeah, it does actually. System of at least two equations with at least two variables. As long as there's two variables, they don't have to, your one equation can only have, you could have an equation with one variable as long as within the system you see two variables. So here's an example of a linear system. So let's do some review. Grab your graphing calculators. Okay, so back in the day, you found the solution to the equation by, what was the first step? So you went to y1, let's clear what's there, and you plugged it in. So 2x plus 3 and negative 3x plus a half. We could graph this by hand, because our y-intercept for the first graph is 3, slope is 2, right? Second graph, slope of negative 3, y-intercept of a half. Okay, what do we do next? Push graph. If your windows are different, like mine, you can reset them by going zoom 6. And all you need to see within your window range is the intersection point. Can we see that? Yeah. Okay, how do we find the intersection? Second, trace. Then we push 5. And then what? We move the cursor over to the intersection point, especially if there's more than one. In this case, there's only one, so it doesn't really matter. And what do we push? Enter, enter, enter. So there it is. Our solution is negative a half, comma 2. Okay, you can also check your solution because your calculator automatically stores your intersection point. We've talked about this, right? No? I don't know. I tell my grade 10s all the time, so sometimes I forget. So if you quit, if I type x, it's stored as negative a half. If I push alpha 1, which is y, it automatically stored the y as 2. So checking my work in my calculator is really easy. So in the first equation, y is supposed to equal 2x plus 3. So we have y, so 2x plus 3. Does that equal my y value of 2? Yes. Left side equals right side. Negative 3x plus a half. Does that equal my y value of 2? Yes, it does. Pretty cool, hey? This is also beneficial because if you get a decimal as your intersection point, you can change it to a fraction. You can go x, math, enter, enter, and that gives me a fraction, negative a half. So that's pretty handy too. If you get like 0.679, right, an ugly intersection point, we can change it to a fraction. Okay, so a linear system usually has one solution. There was infinite and no solutions, which we'll talk about later, but it usually has one. Then we have, which we're going to spend a lot of time on, linear-quadratic systems. And linear-quadratic systems often have two intersection points. Okay, so let's graph them and find them. We have y equals, we'll clear this, x squared minus 4, and x plus 1. Okay, so if I want to find the intersection, and there's two of them, you have to move your cursor. Second, trace 5. So once you get to this point, you have to move the cursor only one time. And then you can push enter 3 times. So we move the cursor to the area we want. So if I want the one on the left, I'm going to move the cursor to the left side. I'll put the LCD up. Okay, so move it over to the left side. And then once you're there, you can still push enter 3 times. 1, 2, 3. There it is. Now, it automatically stored my x and y. So that's negative 1.79. If I want to change it to a fraction, I quit. I could go x, math, enter, enter. Okay, this one can't be changed to a fraction. It's not a rational number. So x was negative 1.79. What was the y value? To 2 decimal place? Negative 0.79. And I'm pretty sure that can't be changed to a fraction. Okay, and now I want the other one. Oops, that's not what I want. I want my rabbit. Okay, so graph second trace 5. Move over to the other side. Enter, enter, enter. So 2.79, comma 3.79. So there's 2 intersection points. Oops. Oops, that's not an eraser. 3.79. Okay? Okay, turn the page. So the third type of solution yeah, I wanted to write some extra notes. Let's leave it. So in a quadratic linear, it is possible to have no solution. So that's if, what does it mean by solutions? When I say solutions, what are we really talking about? Number of intersection points. Good. How do we know if a line is linear? Or the exponent is what? 1. The exponent on the variable, or on x, because we're always dealing with y as the exponent of 1, is 1. And how do we know something is a quadratic? Yeah, the exponent on x, it's a parabola, is 2. It's a degree 2 function, right? Okay, so one possibility is that we can have no solutions. We can have a linear equation and a quadratic equation that don't intersect. And that would be a no solution. There's no intersection point. How would it look if it was one solution? So we're in a linear quadratic situation. How could we have just one solution? Touches only, like at the bottom, yeah, or like a tangent. So if you had a quadratic line, and then you have a linear equation, maybe tangent to it. So that's not tangent. Definition of tangent is it only touches once, right? So that's an example of one solution. How would it have 2? That's probably the most common. Goes straight through and it intersects 2 times. Okay? So another type of system we're going to look at is quadratic-quadratic systems. So what would that look like? 2 quadratics, 2 parabolas, right? Two systems that are both quadratic. So here's an example of a quadratic-quadratic system. What I'd like you to do is find these 2 intersection points on your calculator. Here it is. Okay. Oh, cool. That was awesome. Did you guys just see that? I'll show you it after. It was the coolest thing in the world. Okay, so we have y equals, hey, go away. Y equals x squared minus 5 and negative x squared plus 3x minus 2. Okay, graph that. Okay, so second trace 5. Move your cursor to the one intersection you want. Push enter 3 times. See if this works again. So cool. I just like, that is so cool. Okay, you don't think it's cool. I think it's cool. So did you get negative 0.69 and negative 4.53? So cool. Okay, and the other one, second trace 5. Move your cursor to the one you want. Push enter 3 times. Watch this, watch this. There's the one. Oops, and I just rerun it. That is so cool. Okay, here's the other one. You don't think it's cool, I know, but I'm just like, it just made my day. You have no idea. 2.19, this is like awesome. Negative 0.22. There's our 2 intersection points. Pretty simple. I'm like so happy. A solution to a system is the xy coordinate that satisfies both equations. In other words, it is the point that is on both lines or the intersection. Not too mind-boggling. Turn the page. Okay, so is it possible to have no solutions in a quadratic-quadratic? Yeah. Give me an example what it would look like if you had 2 quadratics not ever touching. One's going up, one's going down, and they don't meet. Good. Is it possible to have one solution? Okay. Give me an example of what it could look like. Okay, so let's say one starts at the origin, and one opens down, and one opens once. So they have like the same vertex. Okay, that's one solution. There's another way we can do one solution. I'm running out of room. I'm going to write it up here. Or you can also have where the 2 lines are almost like what we call parallel, where they have the same, oh, you can't see that. Give me a second. Oh, I want red. I'll move it. Just 1 second. Oh, that's not what I wanted to do. Uh-oh. Uh-oh. Okay, come on. No! Okay, let's redraw it. I'll draw it over to the left. Okay, so another way we could have it is if the A values are the same. So if they have the same A value, it's almost like parallel, the idea of parallel lines. So, and they can intersect once. Okay, so this is an example of one solution where these lines have the same A value. Okay, and so that will also be an example of one solution. And we're talking about the A value in ax squared plus bx plus c. So it's almost like they're parallel. The idea of parallel quadratics, okay? But these ones like meet once, only once. Okay, 2 solutions. That one's pretty self-explanatory. It's probably the most common. Intersect twice. And what would infinite solutions be like? Same line, same quadratics. Yeah, they're identical to each other. So they overlap each other. That'd be infinite. So same line. Okay, methods for graphing, we've talked about tons. So basically the same, just move step 6. Usually we input y1, y2, graph the 2 equations, then we move the blinker. So that should go after step 3. And then we go second trace, and we can push enter 3 times. Okay? To move the blinker before, it's always easier. I guess we should do example 1 because it's good practice to practice graphing by hand. So let's do this one. Let's graph it by hand. So y equals x squared. Where's the vertex going to be? 0, 0. And because we're graphing y equals x squared, what's another point? Negative 1 and 1 and 1 and 1. Because 1 squared is 1. 2 squared is 4, so negative 2 and 4 and 2 and 4. 3 would be up at 9, and negative 3 would also be 9. Oh man, so hard to draw a perfect quadratic. Okay, life is tough, eh? Poor us. X plus 6. How would you graph y equals x plus 6? Grade 10 all over again. Haunting you. Where would you start? 6. Sorry. Specifically, what is 6? Your y-intercept is 6. Okay, that's your y-intercept. What's my slope? Yeah, your slope is 1 over 1 because your coefficient is 1. So we are moving up 1, right 1, up 1, right 1. Look at that. I found one. Oh, I found another. Draw our line. Fun times. It's nice when it works out nicely, hey? Okay, so what's our solution? Without our graphing calculators, if you graphed it nicely, you can see it. 3 and 9. Uh-oh. Okay, sorry. 3 and 9. And negative 2 and 4. Okay, how do we check our work? Let's talk about checks. Plug it into each formula. So y equals x squared does, so we have to check both values. I have to check, does 9 equal 3 squared? Yes, 9 is 9. I also have to check, does 4 equal to negative 2 squared? Yes, good. Then we have to also go to the other equation. It's such a pain in the butt when there's 2 solutions, because there's 4 things we have to do. So does 9 equal 3 plus 6? Yay! Yeah. Does 4 equal to negative 2 plus 6? Yay! So our solution's correct. Okay, we're almost done this lesson. Let's skip the first example and go straight to example number 2. Is that okay? You already did it or what? Oh. I know, it's now you try. So can we skip it? Because I want to do 2 lessons today. Okay. I mean, what are our steps? Do you know what to do? Make it y equals. Yeah, then graph it. This one you'll have to use your calculator for. So. By hand. It would have a nice intersection point if you're solving by hand, yeah. Okay, let's go to example 2. So example 2 is a quadratic-quadratic system. Okay, and it says solve the following by graphically. So what's wrong with our equations? They're not y equals. Okay, so the first equation, how do I make it y equals? Add y. So we're just going to get y equals x squared minus 4x plus 1. Good. And number 2, equation 2, what do we do to get y by itself? Okay, so y is positive. Could we just move everybody else? Yeah, let's do that. So y stays positive. Y equals negative x squared plus 10x and minus 23. Sorry. Okay, now, just by looking at this, will these regular windows work? For the first equation, will it work? Probably. What about the second equation? Probably not. Well, let's take a look, because it has a y-intercept of negative 23, but maybe it'll work. Let's grab our graphing calculators. And I want you to plug them in. Both equations. And then we can get to the fun stuff, which is algebraic stuff. I know. little speech this beginning of class didn't help. Okay, x squared minus 4x plus 1. Okay. Question for you. Graph. Everyone graph it? You good? Okay, who says there's one solution? Anyone? Who says there's going to be two? Ooh. Okay, we have differing opinions. So do our regular windows work for us right now? No. Okay, not really. So these regular oh my gosh, that's not what I wanted. Okay, let's try this again. These regular windows don't really work for us because we can't tell if there's one intersection or two, right? So on calculator right now, it looks like this. It looks like, just roughly sketching, there's one graph and the other graph, and you can't really tell if it's one or two, right? Hard to tell if these have one or two solutions. So what are we going to do? Change the windows. Zoom in. Okay, we need to be sure. Let's change the windows then. Okay, so on my calculator, what should I change my windows to? Where do we want to kind of zoom in close to? We want this area in here, right? That's what we want. So that's between what? Like x. So x, let's do a little bit more, just like, because this is kind of close. Oh yeah, you could do 2. 1 or 2 for x to what? 5. 1, 2, 3, 4, 5. Okay, let's change x1 to 5, and y will go from -4 to like 4. Okay. So we said our windows, we're going to go -2, I think it was, we said x to 5, and then -4 to 4. Okay, so we're changing our windows. Now graph it. How many intersection points? 2. Okay, so I'm just going to write that down. So our windows we did -2 to 5. And y we did -4 to 4. And now our graph looks like, oh, I'm going to do some fancy stuff here. Ha ha. Oh, hey. Now our graph looks like this. So we can see now that there's 2 intersection points. So let's find them now. Second trace 5. Move your cursor over to the first intersection point. Enter, enter, enter. 3 times. Did you get 3 and -2? And the other one? 4. You got 4? Second trace 5. Move your cursor over. Enter, enter, enter. 4 and 1. There you go. Okay. All right. That lesson is done. On to the second one. Hooray. Should I keep recording?
Yes.
I know, I'm just thinking how long it'll take to, how long do we have? We are good for time. I'm gonna